This is Anna. She performs variety of activities and undergoes different emotions throughout the day. All of these leave distinct patterns of brain activity that are signatures of activities and emotions on the different areas of brain. But how do we assess these footprints on the brain? This can be done through this fancy machine that observes how the hydrogen molecules in the brain behave in the presence of a huge magnet. Tracking these molecules helps us track the oxygen consumption of different neurons in the brain over a period of time and thus assessing the brain's activity and its signatures. But these measured signals can get corrupted from structured sources of noise, such as the loud sound produced due to the machine, which could irritate Anna, or some cardiac and respiratory fluctuations like breathing. In addition to these artifacts, measured signal can also get affected by the unstructured sources of noise, which could be due to the electronics of the machine itself or the technology used for the acquisition of these signals, or due to some things that could not be accounted for earlier. At the end, we can only observe the combination of these different signals depicted in blue. Hence, the signal acquired from the machine would be the result of the superposition of the brain signal due to Anna's activities or emotions, that is the signal highlighted in black, due to structured sources of noise, that is the green signal, and due to the unstructured sources of noise, that is the red signal. At the end, we can only observe the combination of these different signals depicted in blue. So, how can we get to the black signal, that is the signal which is the result of the activity in Anna's brain? Various methods have been proposed in literature that talks about the different techniques to model the structured sources of noise and retrieve the signal due to brain activity. Once the signal is free from the structured noise, the remaining step is to remove the effect of unstructured noise, that is the red signal. Yet we do not know how it would look like. But the signal of oxygen consumption from neurons have some specific structure related on how it evolves over time. That is, it has a property called long-term dependency. Simply speaking, the oxygen consumed at a particular sample is dependent on the consumption at the past samples, not just one or two, but many. Hence, limiting the possible changes in the signal observed as it evolves over time. Therefore, we used this property to model the time-evolving signal using a dynamical model known as autoregressive fractional integrative model. This model can be used to filter out the unstructured noise, that is the red curve, in the acquired signal and retrieve the clean black signal. But why do we need this clean brain signal? This is because the signal thus acquired from tracking the oxygen consumption of different areas of brain can aid in providing new therapeutics or better diagnosis of neurological disorders, for example of Alzheimer's, as well as to understand the functioning of the human brain.